Okay, so today we'll do the chapter 12 and the appendix. So the chapter 12 we summarize where the theory applies where. So the main we'll state some main results. So the first example is some hyperbolic report with some hyperideal ends. Where the end waveform is a sphere or a disk as a base space. So for example, if you have a Coxeter 3 waveform, you get a disk. So hyperideal end means that the vertex is outside the hyperbolic space. And so if the end fundamental group is generated by finite order elements, then uh, in this case all the ends has to be lens shaped or horospherical because it satisfies the strong middle eigen strong middle uniform middle eigenvalue condition, right? Because this is one. Okay, so and so then so basically this lambda x denotes the eigenvalue. And so if it is always one, then you say that you satisfy the unit eigenvalue, middle eigenvalue condition for this BE or the RPN structure. So if E is a Tn, then this boundary component is in totally geodesic hyperspace, and it corresponds to eigenvalue one in the dual holonomy. Then we say this is satisfies the unit middle eigenvalue condition. Okay, so this lemma is that if you have a Newton real projective orbital with radial, I should say it's Rn or Tn. Sorry, that should be a mistake. And it satisfies NS, and this E is Rn or Tn, then it's and the primary is virtually generated by finite order elements, or is simple, or it satisfies the unit middle eigenvalue condition. Then E is either a properly convex lens-shaped Rn or lens-shaped Tn, or is horospherical. Or if it has a virtually abelian holonomy group, then it's E is a lens-shaped Rn, or the Tn, or is horospherical. And okay, maybe I don't need the second statement. Sorry, I have to. Right. Anyway, so I should say that this map is a homomorphism, and so it is one for every element if it's simple or is virtually generated by finite order elements. So each Rn is complete or properly convex, but or it is convex but not properly convex and not complete. So if it's complete, then it is either horospherical or it has at most two norms of n, two norms of eigenvalue. So by this NP-NCR case, so since the multiplication by of all the eigenvalues is one, so you have one. So if one of the eigenvalues this is one, then the other has to be one also. So this case cannot happen. So it has to be horospherical in the complete case. And the properly convex, if it's properly convex and uniform eigenvalue condition is satisfied by the remark 532, because if this is always one, then it's just depends on the word length or by the length thing. So it's just length computation. So then by lemma by this theorem is generally length, so the corollary 8.82 case removes that E is convex but not properly convex case. Okay. And it's Tn, and then you can do the dual argument to get these things. Okay. Maybe I don't need this, but I don't. Yeah, I forgot that. So anyway, sorry. So the theorem 12.1.3 is that if you have a strongly tamed properly convex ovipole with Rn or Tn, suppose it satisfies property Ns and is virtually generated by finite or the element is simple or satisfy the unit eigenvalue condition, then holonomy is actually here. So you can put in the U here because we know these are all R-end or lens-shaped, horospherical, or in the R case, it has to be lens-shaped or horospherical. And the horospherical case, of course, is you can easily see that the endpoint is unique because the cusp point group fixes this cusp group fixes unique point in RPN. Okay, and that's clear. And so in the lens case, then the uniform eigenvalue condition with Bx or some other point might hold, but so then this if it's a global fixed point, then I mean the stationary point, then this will be one for all G. Then this shows that it will also act as a lens cone with the vertex at X. But then this theorem shows that there's a unique vertex where this becomes a lens cone. Okay, so that's 5.4.4. So in the Tn case, you always do the dual argument, and this will work the same. Okay, so that's the case, and so combining these all the results like this 12.1.3 and then 11.01 and 6.4, you can show that if it's it satisfied these nice conditions, then the CDEF E is actually CDEF EULH. Okay? And this sends this space to the union components of this, and which is also a union component of this because you can drop the stability and it will still be, this component will always be in the stable. So you can also do the same for S step. So those are the things here. Okay, and right. So for virtually abelian groups satisfy NS clearly. So finite volume hyperbolic before satisfy these conditions also. So you have the corollary that if you have a strongly tamed Cox and ovipole with RNs emitting finite volume complete hyperbolic structure, then this is the same as a component of these, which are also union component of these, and this is equal. Okay. I think you can drop this to hyperbolic with the hyperideal ends as well. Okay, so I didn't do that here. Okay, so that's the thing. So I give you two examples. So Tillman has this. So there's some list of by the hyperbolic ovipole given by Hurd, Hudson, and Martelli. So they have some list of simplest hyperbolic ovipoles. They have computer program to do it, and so this 2H11 is start from some complete hyperbolic tetrahedron with 4 dihedral angle equal to pi over 6 and 2 equal to pi over 3. Maybe it's pi over 3. Sorry, should be pi over 3. And the opposite pair of opposite pair and a pair of this should be a pair of opposite, and then there's a way to glue these two faces, adjacent faces, by an isometry because if you draw this triangle, then you see these two pairs are isometric, so you can glue by a hyperbolic isometry. Okay, and so then they can try to deform this projectively, and Forti and Tillman found the two-dimensional solution, and they show that this has to be convex, and so then we can also show that this is convex using this previous corollary. Okay, and another example is so you take a complete hyperbolic crossover based on convex polytope. So we take a reflection ovipole of a convex tetrahedron orders all equal to 3. So you take a convex tetrahedron with the orders Cox ovipole with orders are equal to pi over 3. So that means angles are pi over 6 here, and then you can take you can double this ovipole, and you get an orientable ovipole. And the end ovipoles are 4 two spheres with 3 singularities of order 3. So this is a 3 sphere with 4 points removed and 6 edges connecting them, or given 3 cyclic group and as local group, or the 3 cyclic group as order 3. Okay. So this is a example of a developing map here. And, so you take this hyperbolic 3 ovipole and you assign R type to each n. Then this actually equal to this, and this maps onto the components of these spaces, and also these. Okay. Okay. And Okay, so the basically the proof is that you look at all the suburb group with fixing points of the Klein model, then these each end is actually virtually abelian. Okay, and so it satisfies NS, and then these are all so pi 1 is relative hyperbolic with respect to fundamental group. Okay, because it satisfies a complete hyperbolic structure, it follows easily from there, and then this S step equals this S step ULH. And so now we can actually use this paper of mine, and then you can give a restriction to the end ovipole. So given a projective structure, you can give a projective structure at this end, and so you can consider the image, and the image in here. So this is a bigger space, and then you can show that this space is obtained by gluing 2 convex tetrahedron, and then you can write this as space of invariance of triangulation. So this is obtained by doubling a tetrahedron with edge order 3, 3, 3. So you can triangulate all into 2 tetrahedron, which gives each ovipole and ovipole this sphere with the 3, 3, 3 singularities. Okay, so there's 2 sphere with 3, 3, 3 singularities. Okay, and then so this has a projective structure, and then they can be classified by the projective invariance, so which satisfy this condition for each of these. Okay, so each of these sphere can be divided into 2 triangles. Okay, 2 triangles, and these triangles will give you this 3 cross ratio at the vertices, and 2 interior invariance at the. So then you can compute these invariants by so their interior. So the solution space is given by the SI and TI, and corresponding to each of these triangles. So I is 1 to 4. I and TI are the parameters of the deformation space of these spheres. And so they have these invariance SI, TI, and so they satisfy this rho and sigma will be given by this. And so for the first triangle, and for the second triangle, you're given by this. And tau is this number. And so this is a union of 4 sphere with singularities. And so in order for it to be in J, then this cross ratio across the edge has to agree. So that's it. This gives you this equation and this equation. Okay. And then there's so the product of the central invariant has to be the same. So these give you these equations, and fortunately these are solvable, and you can get that these are parameterized by S, and this is also given by some CS. So the solution space is one variable, and then there's three variables. So these are all four variables. So it's four-dimensional cell. So it's actually one. So the for solver is only three. So it's one bigger than these dimension. So conversely, if you give these invariants, you can also show that you can glue this back. Okay, so that's how you can get these invariants here. Okay, so then using this you can draw this developing image which tessellates some convex domain, and then these are the radial points. So something that looks like a vertex will be the radial fixed points here. Okay, so there's some tetrahedron that's here, and then the deflected ones, and so on. You can see it a little bit. Okay. Okay, so that's the first part, and I will continue with the next one 5 minutes later.